Hi everyone, my name is Lavija and this is my video for Smart Electrodeposited Alloys Innovative Training Network. Here at the Autonomous University of Barcelona, we are working on smart nano-engineered materials, nanomechanics, and nanomagnetism, and within the scope of my doctoral studies, I am carrying out research on developing protective coatings suitable for sustainable applications. In socio-ecological terms, sustainability can be defined as the pursuit of a common ideal to support the endurance of biological systems. It has three key domains such as environment, society, and economy. When environmental aspects of sustainability are considered, material selection and reclamation efforts are the first points to come to mind, while workforce development and essential training programs form the social aspects of the concept. Of course, capital improvements and new market development are the steps to be taken in order to establish a sustainable economy. In today's fast-moving world, as downsizing is seen in all conventional technologies, microelectromechanical systems, which can be divided into four subgroups such as microstructures, microsensors, microactuators, and microelectronics, have come into focus of novel market development. If we have a look at the fabrication processes commonly used for microelectromechanical systems, we see several coating technologies. Among the chemical deposition methods, electrodeposition, and physical growth methods, sputtering can be given as popular examples. Electrodeposition is a process that uses electric current to reduce dissolved metal cations so that they form a metal coating on an electrode. In a three-electrode electrodeposition cell, working, counter, and reference electrodes take place. The potential is measured between the working electrode and the reference electrode, whereas the current flows between the working electrode and the counter electrode. Sputtering is done by having a target surface bombarded with high-energy species, mostly gas ions, which leads to ejection of a vapor flux to be used as a vapor source for the film growth. So, the question is, how come is it possible to integrate sustainability into novel technologies? The answer lies in sustainable material selection. To develop an idea about this, one should have a look at the directives issued by European Commission. Regarding the current regulations applied, the use of critical raw metals such as rare earth and noble metals is highly restricted due to the fact that they are highly costly and hard to access. Moreover, there are strict limitations on the use of toxic metals such as nickel and cobalt. Among the eco-friendly material choices, we can count the semi-metal bismuth and the metal copper-based materials. For multiferroic applications, bismuth ferrite is a good candidate instead of the highly preferred nickel and cobalt-based ferrites. For shape memory alloy applications, copper aluminum nickel alloys with 5% of nickel can be suggested as a substitute for the widely used nickel titanium with 55% of nickel. When checked out by scan electron microscope, we see that electrodeposited bismuth particles show a morphological variation from hexagons to dendrites as the applied potential is decreased. When X-ray diffraction is carried out for the structures grown at a series of applied potential values, it's confirmed that rhombohedral bismuth is obtained. For several cases, the crystal structure required is obtained by manipulating electrodeposition parameters. However, there are cases in which post-treatment must be used in order to induce crystallization. For instance, 2 hours of equilibrium heat treatment at 600 centigrade degrees must be applied in order to obtain bismuth ferrite crystals with prism morphology. The magnetic behavior of the samples can be characterized by vibrating sample magnetometer. Though antiferromagnetic by nature in bulk, weak ferromagnetism is encountered in nanocrystalline bismuth ferrite due to presence of uncompensated spins in its structure. Shape memory effect is a thermoelastic reversible martensite transformation between the low-temperature martensite and the high-temperature austenite phases. When it comes to copper aluminum nickel shaped memory system prepared by sputtering and heat treatment, the process applied after depositing is quenching in iced water after holding the sample at 800 degrees for 1 hour. The room temperature phase shifts from martensite to austenite due to a gradual change in composition. Quenching as an additional step helps in obtaining shape memory effect. However, is it possible to induce shape memory effect in one step? To figure that out, I made a visit to another partner of the network, University of Cambridge. There, fellow PhD candidate Semerkardi and I worked on sputtering of this system along with in-situ heat treatment. Magnesium oxide with 001 orientation was chosen as the substrate due to being stable at high temperatures and its structure that favors the epitaxial growth of the austenitic phase. It was shown that austenitic copper aluminum nickel could be obtained by this method as well. Moreover, it can be seen that the low lattice mismatch favored the oriented growth of the sample along 100 direction due to presence of strong 200 and 400 peaks in the XRD results. Throughout all these studies, it was shown that bismuth, bismuth ferrite and copper aluminum nickel shaped memory alloys could be synthesized by using coating technologies as sustainable materials for novel applications.